3.1 is quadratic functions. Quadratic functions are of the form ax squared plus bx plus c equals f of x, or we can look at it like this. This looks like completing the square. It's often referred to as vertex form, and I'll show you why in a second. Have the leading coefficient, and then x minus h, the quantity squared, plus k. We're going to start with this one because it is a graph shift of y equals x squared. So if we have y equals x squared, the turning point is called the vertex. The turning point of a parabola and we're going to write that this is graphically known as a parabola. The shape on the graph. The vertex is the turning point, and if we were to consider something like f of x equals negative, let's say x minus 4 squared plus 10, this minus 4 from back in chapter 2 when we talked about graph shifting, inside the parentheses shifts the graph right 4 units. This plus 10 shifts the graph up 10 units. Now if you remember, if you have a negative in front of the function, that is going to flip the graph horizontally. So this graph is going to face down. And we're going to do our best to draw a parabola through there. So that makes the vertex 4, 10. And that's where the graph turns around. So we can start graphing these functions a little easier with if they're in vertex form. If they're not, we have an equation that gives us the x value of the vertex. So if the vertex is h comma k, h is negative b over 2a, and k is f of h, which is f of negative b over 2a. And that's how we can find the vertex if we have this written out and it's in descending order, ax squared plus bx plus c. Okay, let's list some important things about quadratic functions that we're going to study. So we've got the y-intercept is the first thing, and the y-intercept for any function is always f of 0. You plug in 0 for x, you get the y-intercept. And the x-intercepts may or may not exist for a quadratic function, but for any function, to find x-intercepts, you set f of x equal to 0. That's the same thing as saying replace y with 0. And x-intercepts will exist for a quadratic function. This would be if a is greater than 0, so the parabola faces up, and k, the vertex of the y coordinate of the vertex, is less than 0. And the other situation would be if we have a is less than 0, so the leading coefficient is negative. That would make the parabola face down. And if the vertex has a y value greater than 0, that vertex is going to be above the x-axis, so we will have x-intercepts. And what this means is when we go to find the x-intercepts, when we set the function equal to 0, we're going to get a quadratic equation. And if this is the case on the graph, that means that the quadratic equation is going to have two real number solutions, and those real number solutions occur at the x-intercepts. And that's an important thing to keep in mind when solving polynomial equations. The roots of a polynomial equation, provided they are real numbers, are the x-intercepts on the graph of that function. It does not matter if it's a line, if it's a quadratic, third degree, fourth degree, so on and so forth. Okay, let's mention the two situations in which x-intercepts do not exist for quadratic functions. So this would be a positive parabola, so leading coefficient is positive, and the vertex is above the x-axis. And over here, we would have a downward facing parabola, and the vertex is below the x-axis. So what we would have here is ax squared plus bx plus c equals 0 has two complex solutions, non-real complex. So both of these would result in, when you went to find the x-intercepts by setting the function equal to 0, you would end up with the imaginary unit in your answer. And if you didn't already know from, checking the leading coefficient and checking the y-coordinate of the vertex, that would be your clue that x-intercepts do not exist for that quadratic function. So y-intercept, x-intercepts, and then from the vertex, we've already mentioned how to find the vertex. We get the axis of symmetry. We're still going to refer to the vertex as the ordered pair h comma k. The axis of symmetry is x equals h. And what this is, if we had something like this, this is x equals h. The function folded at the axis of symmetry would be on top of itself. And that is always the vertical line through the x-coordinate of the vertex. So we can do the vertex and axis of symmetry. Then we can also mention the domain and range real quick. The domain of a polynomial, of any polynomial, is all real numbers. So that one's easy. And then for the range, if a is greater than 0, that means we have a parabola that points upward. The range is k to infinity, including k. So for the vertex still being at h comma k, we're using that placeholder h comma k. K is the y-coordinate of the vertex. Now if a is less than 0, then the range, this parabola would face down, so if we made a note that this faces up, would be from negative infinity to k with a bracket, which includes k, then we can do the interval that the graph is increasing and decreasing. So again, we can simply look at the leading coefficient, and remember, intervals of increasing and decreasing are written in terms of the x-axis. So we're looking, increasing is where we are reading the graph from left to right and answering the question, where is the graph moving upward as we read it from left to right? So increasing, if the parabola faces up, if a is greater than 0, then the function increases on h, the x-coordinate of the vertex, to infinity. And then it would be decreasing from negative infinity to h. These are parentheses, and in calculus we'll learn why we have a parentheses right here rather than a bracket. But just remember that for increasing and decreasing, you have parentheses. You never use square brackets on increasing and decreasing. So then we have, if a is less than 0, we would be looking at a downward facing parabola. So we are walking uphill from negative infinity to h, and then we are decreasing from h to infinity. And then the next thing is the extreme value, which in this case is an absolute extreme value, and that occurs at the vertex. If the parabola points up, so if a is greater than 0, there is an absolute minimum at h comma k, at the vertex. So we'd be looking at something like this. H comma k is the minimum, and if a is less than 0, we would have an absolute maximum at h comma k. So we'd be looking at something like this. We would have the difference between an absolute minimum and an absolute maximum is here we have an absolute maximum because there are no y values. There are no y values that are greater anywhere on that graph. If we had a function that had turning points and the arrows extended forever, like we will see when we cover graphing polynomials of greater degree, we could have a relative extreme value, but parabolas have an absolute minimum if it points upward and an absolute maximum if it points downward. So let's do an example starting off in vertex form. So let's f of x equals x minus 2 squared minus 16. So let's find the y-intercept, which is f of 0. 0 minus 2 squared minus 16 is 4 minus 16, which is negative 12. So the y-intercept occurs at 0, negative 12. Okay, do these x-intercepts exist without looking at the graph? So the idea is that we learn enough about quadratic functions to be able to graph them. So we can't necessarily just look at the graph and answer that question yet. So as of right now, the most efficient thing would be to notice that this is a positive leading coefficient, and the value for k, the y coordinate of the vertex, is below the x-axis. So we could say parabola faces up, vertex below the x-axis, so we know that x-intercepts exist. Now, for the purpose of graphing, in this quadratic functions, if we're answering the question, do the x-intercepts exist, we first find the x-intercepts, we need to know if they exist first. In this section, it's not super efficient to go and solve for non-existent, pure complex answers when we're only trying to graph, in the real number system. So now that we know that they exist, we'll just set the function equal to 0. And solve, and we will get the easiest thing to do. This is why we kind of mentioned it's called completing the square form. The easiest thing to do would be to isolate that perfect square root. When you square root 16, make sure you understand that since we're solving an equation, that could have been, that positive 16 could have came from plus or minus 4. So we have to have that plus or minus. So the x-intercepts are at 2 plus 4, which is 6, or 2 minus 4, which is negative 2. So we do have x-intercepts. Let's find the vertex. And we are looking at a function in vertex form. So that's kind of nice because it's just staring right at us. Now the generic is x minus h. So since it's x minus h, we need to, so that's x minus 2. So the x coordinate is 2. And the other thing is, remember back to graph shifting, if we have x minus a number inside the parentheses, that's going to shift right. So that's going to take us from 0 on the x, shift it right, we're going to end up at 2 on the x. This negative 16 on the outside is a translation downward by 16 units. So if we started at 0 on the y, we have a negative 16 right here. That's going to take us down the y-axis to negative 16 on the y. So there's our vertex. The axis of symmetry is x equals 2. It's always written as the equation of a vertical line through the x-coordinate of the vertex. The domain is all real numbers, and then the range, since we have a parabola that points upward, is negative 16 to infinity. This function is, since the parabola is pointing upward, this function increases from the x-coordinate of the vertex to infinity, and it decreases from negative infinity to the x-coordinate of the vertex. Since the parabola faces up, we have an absolute minimum, so we have a low point at the vertex, 2, negative 16. I like to give the ordered pair. That gives us all of the information, but it is also acceptable to say the absolute minimum is negative 16, the function value. So it's saying that we have a least function value. The ordered pair tells us the value that the least function value occurs at, so the x value, and then the minimum function value. So we have all that information. We're going to graph it. So think of it as taking the parabola starting at 0, 0, shifting 2 to the right and down 16. So I'm going to plot the vertex at 2, negative 16. And we have a y-intercept at negative 12. So I'll plot that. We have an x-intercept at negative 2 and an x-intercept at positive 6. And I'm going to do my best to draw a parabola. So that's negative 2 on the x, that's negative 12 on the y, that's 6 on the x, labeled the vertex, and we have a properly graphed quadratic function. Label your axes, and you're good to go. Okay, let's take a look at another example. So let's say f of x is negative x squared minus 7x minus 10. And rather than having this in vertex form, we're going to need to find the vertex using h equals negative b over 2a when we get to that point. So the first thing, let's do the y-intercept, which is f of 0, which is negative 10. So 0, negative 10 is the y-intercept. And the x-intercepts. The x-intercepts, since this is not in graph shifting form, remember we were talking about the k being the y-coordinate of the vertex. Now this is ax squared plus bx plus c. That negative 10 is not the y value of the vertex. That is the constant term for the function. So x-intercepts, whether they exist or not, if it's written out like this, it's not as immediately obvious unless you want to complete the square and put it in vertex form. Most of us don't spend the time to do that. We generally, if it's written as ax squared plus bx plus c, you can check to see if this has real number solutions. So if b squared minus 4ac is greater than 0, this will have real number solutions, and this is the case for this quadratic equation. So we will have two real number solutions, which means the x-intercepts do exist, and you can just check b squared minus 4ac from the quadratic formula. If this were negative, you'd have a negative under square root in the quadratic formula. So we have an example here that factors nicely. We don't actually have to use the quadratic formula if we don't want to. So we have x-intercepts at negative 5, 0, and negative 2, 0. So negative 5, substitute negative 5 in right here, and you get 0. Substitute negative 2 in right here, and you get 0. So these two ordered pairs are where the x-intercepts are. And let's do the vertex. So the vertex is negative b over 2a for the x-coordinate. So negative of negative 7 over 2 times negative 1, which is negative 3.5. The y-coordinate of the vertex means plug in the x value and you will get the y value. So we're just getting an ordered pair on the graph. So this is the same thing as saying f of negative 3.5. So we have replace anywhere there is an x, we need to replace it with a negative 3.5. Careful with negative signs. And for the sake of saving some space on the page and trying to reduce as much clutter as possible, even though there's a lot of clutter on these types of problems, when you plug in negative 3.5 into this function, you get the output of 2.25. So the vertex is at negative 3.5, 2.25 on the y. That means the axis is x equals negative 3.5. Now this parabola faces down, so the range will be from negative infinity to the value k, which is 2.25, and we do include that in the range. We do have a defined ordered pair at 2.25 on the y. And the domain is all real numbers. This function is increasing since it's facing down, we're walking uphill from negative infinity to negative 3.5 on the x, and then we are sliding downhill from negative 3.5 on the x to infinity. And this graph has an absolute maximum at the vertex. Since it faces down, we have a hill, we have a tallest point, and the ordered pair for that is negative 3.5, 2.25. Again, that occurs at the vertex. So let's graph this. I'm going to label the vertex. And we have y-intercept at negative 10, x-intercepts at negative 5, negative 2. Do my best to draw the shape of a parabola. Label my axes. And we've got it graphed.